All right, let's dive right into this explainer. We're going to see exactly how a single, seemingly obscure math theorem from way back in 1992 is actually the undisputed mathematical bedrock powering today's most advanced LLMs, like ChatGPT and DeepSeek. You know, if you've been watching the AI space lately, you've probably heard an endless stream of acronyms: PPO, DPO, RLHF, GRPO. They sound like entirely different beasts, right? But they all share a common ancestor. So today, we're going to unpack that exact ancestor. We're going to stop estimating value, parameterize the policy directly, compute the gradient of expected return, and literally step uphill. Because we're unpacking some pretty dense machine learning concepts today, here's a quick map of where we're headed. The engine of modern AI, the continuous action problem, the policy gradient theorem, taming variance, building it from scratch, and finally, its role as the ancestor of LLMs. Let's get to it. Section 1, the engine of modern AI. We're starting right at the top, looking at how Ronald Williams' 1992 reinforce algorithm is basically the reason every modern LLM reinforcement learning loop even exists. It's honestly mind-blowing that a paper published decades before the deep learning boom holds the exact mathematical key to training AI to reason and follow human instructions. Section 2, the continuous action problem. To really grasp why policy gradients were such a massive breakthrough, we have to talk about the fatal flaw in the older methods. Before reinforce took over for complex problems, everybody relied on value-based methods. Think Q-learning or DQN. And those methods work by parameterizing the value function itself. To make a move, you evaluate all possible actions and just pick the one with the highest expected value. That's an operation called an argmax, which is great if your environment only has discrete actions, like just moving up, down, left, or right on a simple grid. But here is the rhetorical trap that completely breaks value-based methods. What happens when your actions are continuous? Imagine a robotic arm with 10 different joints, and every single joint needs a precise, continuous torque value. How on earth do you calculate an argmax over a 10-dimensional, continuous space in real time? Well, you can't. It's impossible. And on top of that, an argmax is strictly deterministic. If your environment requires a bit of randomness, a stochastic policy, to explore effectively, Q-learning is just going to fight you the whole way. And this is what illustrates the big paradigm shift. The difference is stark. Instead of estimating a value and just blindly grabbing a deterministic action with an argmax, policy gradients take a totally different route. We parameterize the policy itself as a neural network that outputs a probability distribution over our actions. And then, we just sample from that distribution to act. No argmax, no complex Bellman recursion. We simply compute the gradient of the expected return with respect to our network's parameters, and we do gradient ascent. We literally just step uphill toward higher rewards. Section 3, the policy gradient theorem. Now, what's genuinely fascinating is how we actually figure out that uphill step. We completely bypass the Bellman recursion and just compute the gradient of expected return to physically push our model uphill. Okay, don't let the calculus scare you off here because the underlying mechanics are actually incredibly elegant. This formula is just telling us that the gradient of our objective, our expected return, is totally computable. In plain English, you just run an episode and calculate the total discounted return. That's the ultimate treasure at the end of the run. Then you multiply that return by the gradient of the log probability of the action you took at every single step. Average those out and update your neural network weights in that direction. You are quite literally turning up the probability dial on actions that led to higher returns and turning down the dial on actions that led to lower returns. So the absolute linchpin here is something called the log derivative trick. It's the piece of mathematical magic that allows a simple two-line algebra proof to revolutionize AI. See, when you differentiate the expected return, you hit a wall. The probability of a trajectory depends on your policy, sure, but also on the environment's transition dynamics. And we don't know the environment's dynamics. But by using this specific log derivative trick, we can restructure the math so that the environment terms completely vanish. Poof! We're left with a computable gradient that only depends on our policy network. It is mathematically beautiful. Section 4. Taming murderous variance. So despite its theoretical beauty, vanilla reinforce has a pretty fatal real-world flaw. In practice, returns are incredibly noisy. The gradient of your log probabilities is noisy. And when you multiply two noisy things together, the result is absolute chaos. If we just ran the pure math we just talked about, it would take thousands upon thousands of episodes to learn even the simplest tasks. So here is the laundry list of catastrophic pitfalls you're going to encounter out in the wild, alongside the specific, heroic interventions we use to fix them. Returns can get huge, causing exploding gradients. The fix? You normalize your returns across the batch. What about entropy collapse, where your policy gets cocky, stops exploring, and gets permanently stuck? You fix that by adding an entropy bonus to force the model to keep looking around. And because vanilla reinforce is horribly sample inefficient, it basically throws away data after one update, the field eventually developed off-policy corrections like importance sampling, which, by the way, is exactly how modern algorithms like PPO operate. Let's look closely at how combining two of these powerful variance reduction tricks directly created the ancestor of modern actor-critic methods. First up, baseline subtraction. If we subtract a baseline value from our return, like say an estimated value of the state learned by a separate critic network, we drastically cut down the variance without biasing the gradient. Second is reward to go. Vanilla reinforce uses the total return of the entire episode. But logically, an action taken at step 10 cannot possibly affect the rewards you already got at steps 1 through 9, right? Those past rewards are just zero mean noise for your current action. So by tweaking the math to only multiply our gradient by future returns, the reward to go, we clean up the signal immensely. Section 5. Building it from scratch. Time to get visceral and translate all these Greek letters into physical code. We're going to step through building this so you can literally feel it in your fingers. Because knowing how to code this is the prerequisite for understanding everything in modern AI, reinforcement learning. As we walk through these implementation steps for getting a simple grid world running, the progression is super logical. You build a softmax policy network, a simple linear one for a basic game, or a convolutional neural network for an Atari game. You sample actions and capture their log probabilities during a rollout. But please, burn step 4 into your muscle memory. The reinforce update for a softmax policy ultimately boils down to a beautifully simple gradient, the one-hot encoding of the action you took minus the model's output probabilities for all actions. That single calculation is the absolute heart of softmax policy gradients. Finally, you throw in a running mean baseline to stabilize the learning and watch the required episodes to converge absolutely plummet. Section 6, the ancestor of LLMs. Finally, let's look at the immense legacy of this math and see exactly where reinforced lives in today's AI landscape. You might think a 1992 paper is a relic, but it's literally the foundational layer that everything else rests on. This is the ultimate AI cheat sheet right here. Just look at the derived method column. Doing continuous control? You're probably using PPO or soft actor critic, which rely on a Gaussian policy variant of these exact gradients. Training a massive LM to follow human feedback? That is RLHF, which heavily utilizes PPO with a KL penalty. DeepSeek's crazy advanced reasoning capabilities? They use GRPO, which is essentially just reinforced with a group relative baseline and no critic network. Even direct preference optimization, or DPO, is basically reinforced rewritten as a preference likelihood loss, without the live sampling. Almost every groundbreaking paper you see is just a set of brilliant variance reduction tricks built on top of Williams' original theorem. When you read this exact line in a cutting-edge training script today, you are looking at the foundational heartbeat of modern AI. It's reinforced with a baseline. The advantage is just your return minus your baseline multiplied by the log probability of the action. That's it. That simple line of code is actively training the most complex, intelligent systems humanity has ever built. So, as we wrap up this explainer, I want to leave you with this thought. We've completely decoded the engine. You now know that beneath the massive billion-dollar data centers and trillion-parameter models, there's just an elegant mathematical trick from 1992 quietly computing the gradients of expected returns. The fundamental math is solved. The real challenge now is implementation, variance reduction, and massive scale. So now that you truly understand the engine, what are you going to drive it to build next?